Okay, friends, in this video I will touch upon the concept of switching in sine graphs. Even though the concept of switching we can have in all the three structures, sine, gain and skew gain graphs. ഒന്നാം ഭാഗമായ ഈ വീഡിയോയിൽ ഞാൻ സൈൻ ഗ്രാഫിൽ സ്വിച്ചിങ് എന്നതിൻ്റെ ആശയം അവതരിപ്പിക്കുകയാണ്. Switching in sine graphs. So this is the definition. Let sigma VE small sigma be the given sine graph. That means we have the underlying graph with vertex at V, edge at E and the sining function sigma. So such a sine graph is given to us. By switching we mean a function zeta from the vertex set to the group 1 minus 1. So I mentioned the group here because this notion will be extended to gain graph by replacing that group by gamma. Okay, so remember this sigma is a function from edge set to minus 1, 1, whereas the zeta is a function from vertex set to 1 minus 1, such that sigma is switched to a new sine graph, sigma zeta, with the same vertex at V, same edges at E, but a new signature function, sigma zeta, obtained with the help of this zeta, where the sigma zeta and sigma are related by this relation. That means sigma zeta of the edge UV will be the previous signature pre-multiplied by zeta of U and zeta of V. This is how we construct a new sine graph. So we say sigma is switched to sigma zeta. Sigma is switched to sigma zeta. So that's the concept of switching in sine graph. Let me illustrate. Here we have on the left side a given sine graph sigma with two negative edges and one positive edge. Okay, now I am switching this sigma to sigma zeta. You see here in the switched graph all the edges are positive. The question is, natural question is, what is that switching function zeta which converts the given sigma to sigma zeta? Let us go to the picture once again and let me put some see, zeta is what? Zeta is a function from vertex set to 1 minus. So I will be putting here plus 1 here. I see zeta of U is 1 now. Zeta of V is also, I'll be putting 1. So that this edge symbol, let me mark it by some other, okay. This is 1. Edge UV has the signature 1. So 1 into 1 into 1, that is this 1. This 1 into 1 into 1 is this one. Now multiply, see I have to mark here, for W also I have to put some symbol. So let me put it as -1. What will happen here? So Zeta of u is 1, zeta of v is 1, and zeta of w is minus 1. Then multiply this 1 with this minus 1. This is minus 1. This edge is minus 1. So 1 into minus 1 into minus 1, it is plus 1. So that's this edge actually. Then minus 1 into minus 1 into plus 1, that is this one. Therefore, this is having 1, this is 1, 1. See, UV in the new sigma zeta has the signature sigma zeta. Sigma zeta has sigma zeta of UV is equal to 1, sigma zeta of VW is 1, sigma zeta of. So, the what is given sine graph is switched to a new sine graph. A switching function, remember, is a function from the set of vertices to the group 1 minus 1. Okay. Now, there is an important application of the switching which characterizes balance. Balance means all the cycles will be having net product as 1. If you have a cycle, let me take the cycle as this one. Here the edge symbol is 1, edge is 1, here it is minus 1, here it is minus 1, 1 into minus 1 into minus 1, it is 1. Okay, so this is an example of a balanced sine graph. Then one more example, you see this one. There is no cycle. If there is no cycle, it is already balanced. If there is a cycle, the product of the edge symbols must be 1. Such, see for example, another one. This is unbalanced. Look at the outer cycle. Outer cycle is positive. But here is a cycle. This is this triangle, let me take this one. This is negative. Moreover, the other triangle, that is also negative. Why? 1 into 1 into minus 1, that's negative. So, existence of at least one negative cycle will make it as unbalanced. So, this is an example of an unbalanced cycle, unbalanced sine graph. So, if all the cycles are positive, then only it will be balanced. So, to checking whether what is that sine graph is balanced is require the what is the process of finding the net sine of all the or the product of the sine signatures on the cycles, if we have to compute all those things. But this says that a sine graph is balanced if and only if it can be switched. It can be switched to an all positive sine graph. That means all positive sine graph simply means that sigma is somewhat identical to the ordinary graph G. So this is an example of a balanced sine graph. This is negative, this is negative, this is negative, this is negative. So 4 negatives totally it is 1. This negative into this negative into this negative into positive. So actually this triangle will give you actually negative, negative, net, positive. So every cycle you can say it is having signature 1. Now you can see that this given sine graph can be switched to an all positive sine graph. So you can see, let me mark here minus 1. This is minus 1. The edge is minus 1. This is minus 1. Sorry. Yeah, so this is plus 1 because I have to make it as minus 1 into minus 1 into plus 1. That is this plus 1. This is plus 1. Then I have to put a symbol here. Already this is minus. So I have to put a minus here. Then only totally it will be minus. Therefore, this will be positive. Then I have marked first U, then V, now W. I have a choice of X alone. Let me put it as this is minus, this is also minus. I have to put it as minus. then this minus 1 into minus 1 into, sorry, this must be plus, this must be plus. So this is because minus 1 into plus 1 is plus. So you can see that these, see, zeta of u must be minus 1, zeta of v must be plus 1, zeta of w must be minus 1, zeta of x must be plus 1. So that using that zeta, you can make this sine graph, the given sine graph, which is balanced to all equivalent to, switching equivalent to, we say, switching equivalent to the all positive sine graph. So that completes the video.